Okay, welcome back to review, and this is Unit 7 and 9, Day 1. So we're going to split this into 2 days. So you'll hear my voice for 2 nights. All right, so for the next few examples, all this wants us to find is state the transformations, what would the rate of growth or decay be, and what is the domain range in the equation of the asymptote. Now remember, exponentials always have a horizontal asymptote, so the asymptote equation is going to be y equals. So for each state the transformations, I noticed that 3 is going to be a vertical stretch. And it's going to be a decay because the base is less than 1, so it's a decay. And because it's 1/4, that's the same thing as 0.25. So the rate at its decaying is 75%, or a rate of 0.75, because it's always based off of 1. What is the domain? Domain will pretty much always be all reals, and the range will be based on the asymptote. So since there is no vertical shift up or down, it'll be 0 to infinity, and the equation of the asymptote will be y equals 0. So now let's skip ahead to, let's say, the third one. Well, let's do part of the middle one. It would be reflected because of the negative, a vertical stretch because of the 4, and it will be shifting to the right because of that -1 in the exponent. The asymptote will still be y equals 0, but this time it's a growth. Now again, if it's based off of a 1, a 2 means it will be a growth with a factor of either 1 or 100% growth. All right, last but not least, we have a vertical shrink from the 2/3. We have an up 9, which means our asymptote now will be at y equals 9. And it's a decay with a rate of 60% decay. All right. Now, if you see a negative sign, a lot of times the Regents will ask you questions like, which of the following is a growth or which of the following is a decay? Even though this is 1 minus 3, which is 0.7, because it is raised to the negative x power, we know that negative exponents actually reciprocate or flip. So if I type in my calculator, 0.7 raised to the negative first power, it actually is going to give me a growth base. It will be greater than 1, which will make it a growth. So just watch out for that. Same thing with this one. 4 to the negative second power is actually going to be 1/16, which then, again, makes it decay. Number 2 is looking for a regression equation for an exponential. It tells me it's exponential. It tells me what to round to. All you have to do is remember your calculator steps. You're going to type these in L1 and these in L2. So you're going to do stat, edit, type in the things in L1, type in the other things in L2. Okay, so I went to stat, edit, typed in my things in my list, tried to save us some time there, stat, calculate, and then if you scroll down or press option 0, it says EXP-REG stands for exponential regression, hit enter a couple times. Make sure there's nothing in your frequency list in your calculator, because this one does not have a frequency. And it will give you the A value and the B value, so round to the nearest hundredth. It looks like it's going to be about 5.17, 1.09 to the x power. So just to kind of flash that again, you can see where those numbers are coming from. All right, rewrite each of the following as an equivalent. So remember, if we have x to the, let's say, b over n, that's going to be x to the power, and then I take the root of it. So the denominator will be your root, and the numerator is your power or your exponent. Negatives reciprocate, so I'm not going to do the first 4. I'm going to jump down to the more complicated ones. Notice the y is the only thing being raised to the negative 3/2 power. So if the x stays in the numerator, the y is flipping, and it will be power over root. In this example, just the m is going to be changing, and again, a negative just tells me it's going to flip to wherever it's not. So in the numerator, it would be m to the first power, and I take the square root of it, all over 2 still. And if this wants me to write it in terms of a fractional exponent, this would be x to the 4/5 power, but because it's in the denominator, it has to be negative. So if it ever asks you to prove, a lot of times they like to do like show that this is equal, or explain, or justify, something like that. You would just say something like, since m to the 2, oh, sorry, my pen's messing up, 2/5 can be written as m squared to the 1/5, since we can use power over root to rewrite as m squared, and I take the 1/5 power of it. All right, moving on to some logs talk. Now remember, exponentials are just the inverse of logs and vice versa. And there are two different types of logs that we've covered this year. The first one is called a common base log, and that's when, if there's no base written, we assume it's a base 10. And you can confirm this by just doing the lasso method really quickly. 10 squared is 100. The other one is if you ever see a natural log, so ln, the base is an e. So the invisible base that would not be written for a natural log would be an e. So the first thing that we want to review is something that we called the lasso method. You always take the base of your log, lasso it up to the answer, and then you can either solve for x in this case, in the problem, or wherever the variable happens to be, or it could be just like a prove or a simplify. So you always take the base, lasso it to the power, and if you can, solve for x. Now we always lasso a log, all right, but you cannot lasso an exponential. So we came up with a different acronym for that one, and that's the one that we call BAP. So remember, BAP stands for base, answer, power. So if the inverse of a log is an exponential, then the inverse of an exponential is a log. So if I need to rewrite this exponential as a log, it has to have the word log in it. So if it starts as an exponential, it turns into a log with a base of 6, the answer is x, and it's equal to the power. So hence the BAP part. If this one bothers you as it's written in the reverse order, just rewrite it. It takes 2 seconds to rewrite it, and then you can do log, the base of the exponent, the answer, and then it's equal to the power. And then, again, if this is a base e, then we're going to use natural log of a base e, answer, power. If we want to evaluate a log, we actually can, if it's already isolated, if the variable is already isolated like this first example is, we can type that in our calculator. And so if you go to math, you can scroll down, 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 down. Okay, and oops, and the option that says log base, it's letter A. So some of my students determined that if you hit math, alpha, math, it'll jump right to it. But if you hit that, you should be able to just plug in the numbers in the exact places as you would see them written on your page, and you can evaluate the log if you'd like. Same thing for natural log. Natural log is on the left-hand side. It has its own button. It's right above the storing key or to the left of the for button. And then E is second dividing sign. That's where your E button is. Hit enter. And then this one, since I can't type this in because the x is not isolated, we might want to do the lasso method here. So x squared is equal to 36. If I square root both sides, normally I would get a plus or minus 6, but you cannot ever have the base of a log be negative, so you would only have the one solution. All right, moving on to graphing this next section. We are going to graph the log, and then we're just going to talk about the whole asymptote thing. So in this log here, log base 2 of x, if we type log base 2 of x in our calculator, we go to our table of values, and what you'll notice is there's a bunch of errors. And that's because, remember, a log has a vertical asymptote, and since there's no horizontal shifts, our asymptote is going to be the y-axis here. So if I go back to my graphing calculator, I'm only going to plot the nicer points. So I'm going to plot 1, 0, 2, 1, and so on. So let me write those down. Oh, my pen. 1, 0, 2, 1. We have 4, 2, and 8, 3. So 1, 0, 2, 1, 4, 2, and 8, 3. So it does not look like a square root. You have to make sure that you draw your log all the way down its asymptote line, okay? Now, the whole point of graphing both of these is because, well, they are inverses of each other. So 2 to the x, if I do that in a different color, all it does is it takes the same points and just flip-flops them. So f of x is going to be 0, 1, 1, 2, 2, 4, and 3, 8, and that should be the reflection over the line y equals x. So that should be our inverse graph, which you probably learned about or reviewed about a couple days ago. And that has a horizontal asymptote, so that one will never equal the x-axis. So if we know that there is an asymptote at x equals 0 for a log, explain why. Well, it's because the exponential has an asymptote at y equals 0 and is then reflected. All right, we are in the home stretch here. Finding inverses of logs and exponentials. So when you are finding the inverse of these logs, remember it starts the same way. You switch x and y. That's always your first step when finding the inverses. And then to isolate y again, it's in the exponent. So that means I need to BAP this. So log, your base is a 2, the answer is an x, and it's equal to the power. And then I would literally just isolate the y. So the first thing I would do is subtract 5 to the other side. Log base 2 of x minus 5. And then I have it equal to negative 8y. So divide everything by negative 8, and there is your inverse. The middle one's even easier. If you switch x and y, remember f of x is just another way to say y equals. So x is equal to log base 4 of y, and then you just lasso that up. 4 to the x is equal to our inverse. The last one I'm not going to do, it's just too much. My pen is too thick to try and fit that in. All right, so create a table and graph the following exponential. So if I'm graphing the following exponential, the first thing I want to do is figure out what my transformations are. So these two values that are at the end there, the x plus 1 is going to tell me that it's being shifted to the left 1. And the plus 3 is going to tell me it's shifting up 3. And if it's shifting up 3, that's the equation of my asymptote. So that's probably the first thing I'm going to try and plop in my graph here is I have an asymptote at 3. Domain is going to be all reals, pretty much always. Range is going to be from the asymptote up, so 3 to infinity. And if I type this in my calculator, and I use 0.5 instead of 1/2, because if I use 1/2, my values in my table will come out to be fractions. And I think it's easier to graph when you have decimal values. So from -5 to +2, I'm going to fill in my chart here. And plot the points. And notice my y-intercept is 3.5. There will not be, so it does not exist, an x-intercept because we have an asymptote at 3. And so if I take the time to plot these points, -1, 2, 3, 4, 5, all the way up 19, that goes just slightly off the grid there. -4, up 11. All right, there's my points plotted. I'm going to connect them with a nice curved line. Remember, don't go below the asymptote. It should scoot right on top. It was a decay graph, and then it's asking us to algebraically find the inverse, so this is the last piece that we'll do today. So remember, you always switch x and y, so that's step 1. Now, to undo an exponential, normally I would lasso it, and I will in a minute, but I can't lasso until I isolate the exponential. So the first thing after I switch x and y is get the exponential isolated. Now I can lasso this, so BAP this. So log base answer power, and then the last step is just move that 1 over to the other side and you'll have your inverse. base 1/2 of x minus 3 minus 1 is equal to the inverse. All right, see you tomorrow.